Thank you so much, everybody, for being here. My name is Andy. I am one of the librarians here at Thomas Memorial Library. Super glad that you are all able to make it here with us this evening. And I am going to introduce our guests for the evening. We have Russ Pinizzato and Ara Jerahian from the Southern Maine Astronomers Club. And we are super glad to have them here. And I am going to hand it over to Ara. Welcome, Ara. Thanks so much for being here.
Thanks, Andy, and thank you and the library for hosting these wonderful events and allowing us to be on here and share with the community. I think I want to say that I think we're trying to do this virtual star party over Zoom because they have been so far very successful on a regular basis. I think what did we decide, Andy? At every 5 months, I believe.
I believe I can't remember if it was every 5 or every 3. I think we set
every
on,
3.
Yeah.
And on a regular basis, we'll try to stagger them at different times of the year because at different times of the year, different constellations and different targets are up in this night sky. So we'll be able to see different things. So this is our second one that we've done so far. And we took a slightly different route with this one. We have a theme on today's talk, and that theme, as you can see from this first slide here, is the birth and death of stars. So what we're going to show you is 3 targets. Hopefully, one of them I haven't even seen myself through my telescope, so that'll be, total caveat. It could be a disaster, and we wouldn't really be able to see anything because it's a faint target. But we have 3 targets that we'll go through, and we'll walk through them. Along with me, as Andy said, is Dr. Russell Pinizzato. He's a provost of Simmons University, and he's here to both help in the presentation towards the latter end of it, as well as answer some of the more difficult questions that I personally won't be able to answer, hopefully. So here we go. So the first, oops, let me move this to a different spot. Sorry, immediate technical difficulty. We'll just shrink this a bit. So the first thing we're going to talk about, and we won't belabor the topic or the physics behind it, we'll just make it the fun parts of all this, the birth of stars, right? So this is what's called an infrared image of one small part of the target we're going to image, the first target we're going to image tonight. And this is obviously by a space telescope. It's the Herschel Space Telescope, which images targets in infrared. And what does that mean? Infrared is beyond the red spectrum of optical or visible light that we see with our eyes. It's a spectrum of light that we actually cannot see. Infrared is often felt by heat, but it's also just a longer wavelength than red. And what does longer wavelength mean is it actually, when you have an infrared camera, you can detect those longer wavelengths that you wouldn't normally be able to see with your eyes, with the sensor, with a camera. And those longer wavelengths are able to cut through dust and gas, very dense dust and gas, as you can see here up in space. This is an actual image, an infrared image by the Herschel Space Telescope. And the reason why we're showing you this image is because in these types of nebulae, so these gas and dust formations are called nebulae, and in these dense concentrations of dust are where stars are born. And if you look here, these larger blotches of light here, these are where some of the massive stars are actually being born inside of that dust column or dust cluster. These particles of dust, it may boggle the mind to think that a star would be born from dust, but particles of dust just clump together over millions and millions of years, and they compress because of gravity, and they just compress more and more, and the pressure builds up and the heat builds up inside, and the two work together to ultimately one day the star would be born. So the gravity gathers the hydrogen gas and the dust, and the clouds grow denser, and as it squeezes it down, the hydrogen gas heats up to in the early stages of a star birth, heats up to 15 million degrees in temperature Celsius. So that's kind of the baseline, all right? We're talking 15 million degrees to just get the initial kickstart of the engine of a star to get going. And then this nuclear fusion, this thing that takes hydrogen gas, which is the simplest of our elements, right? I know we know helium for those of us who've sucked in the helium from a balloon. We know what helium is because it makes our voices squeaky. And hydrogen is the one element before that, the simplest element. And that is the large portion of most of these stars that initially form. So that nuclear fusion turns that hydrogen into helium and ignites a star. That's basically the engine of a star. Now, as Dr. Pinizzotto has always drilled into us, the magic word of astronomy is gravity. None of this would happen without gravity. Gravity is the thing that forces all these things to come together, forces that heat to build up based on the mass of the matter that's being collected, and allows these stars to be born. So we're going to go right into our first image. There'll be plenty of time, I think, hopefully at the end, to allow for questions if you have any. So either write them down or try to keep them in memory. All right, so first image, so I'm going to get this rolling. I'm going to take 1 10-second exposure, and then you'll see, and then we'll get it going after that. All right, so now I'm going to switch here, browse, images, Rosette, this one, this one, this one. Okay, now this is going to be coming through live, okay? So initially it's going to look not all that great. So we're going to need to stretch the image. So you see, this is where everybody can see this. Andy, you can see this image here, right?
Yes, absolutely.
Now, it looks very grainy, as you can tell, right? It looks very, very grainy. And we have, oh, sorry, one sec. Maximum. The new images will be coming through. And as they come through, this image will clarify. So what am I showing you here? So that I remember I told you that the initial part, that the previous image that I showed you was one small part of this taken with a space telescope. We're now taking this with a telescope that I have here in my observatory in Cape Elizabeth. And we'll just give it a little bit more time. Sorry, one sec. Yep, okay, good, we'll play. All right, we'll give it a little bit more time for the images to start collecting. And as you can see, some of the noise is already starting to disappear, and it's starting, the dust pillars and some of the structures are starting to appear. Let me just make it a little bit brighter. So now what am I doing here? I should have explained that a little bit as this was coming in. So I'm taking images, 10-second images with my telescope sitting right outside of my front yard. And each image that's coming through, the computer is stacking them. And what that means is it's basically averaging frame by frame by frame. And by averaging it, the signal starts to come out, and the noise starts to go away. So what I'm doing here as this is happening is I'm trying to get just the right amount of detail to pop out so you can see the structure. And this target is called the Rosette Nebula. And as you can see here, it's shaped like a rose. Can you kind of start making that out? And this is a huge area of dust and gas. So it's largely hydrogen gas with some oxygen and sulfur in there. And it's in this constellation Monoceros, which basically means unicorn. And in here, in this center, are a cluster of stars. These are hot young stars that have been born out of, let me zoom in on those a little bit. These are some hot young stars, and they don't look very exceptional here, but believe me, these stars here are in the center of this hydrogen cloud, which is about 5,200 light years away. It's in our galaxy, okay? 5,200 light years away. and it's about 130. This whole structure is about 130 light years in diameter from end to end. That's about, if you look up on the sky and you take 5 full moons and put them side by side in the night sky, that's how big this structure would look in our night sky if your eyes could make it out. Here we're using a telescope and a sensor to be able to see it. So as you can see, some of these details are really starting to come through now. And so going back to this hydrogen gas is you've got these stars in the middle that are born out of this gas, as I described earlier, right? So they over hundreds of millions of years, even a billion years, these things will ignite and be born. And these are some of the largest stars we know. These are what are called O-type stars, not important, but they're hot, young, blue stars. And these stars don't last as long as our sun would. Our sun is expected to last a total of 10 billion years, and it's about halfway through its life right now. It's got another 5 or so billion years to go. These hot stars last on the order of millions of years. So they don't really, they burn through their gas and hydrogen. They burn really hot and really fast, and they burn through and have exceptional deaths. And we'll talk about the deaths in a minute. This is the birth portion here. So as these stars are born out of this gas, they start to ignite. They produce a lot of energy and a lot of what's called stellar wind. So their energy radiates outward, and they blow the gas around them and around other stars away from them. That's why you see this cavity carved out the center of this hydrogen gas, of the center of this nebula, and leaving it to look like a rose. And it's called the Rosette Nebula. Now, this is a black and white image, but if you see an image of the Rosette Nebula, it's quite beautiful and colorful because it has a mixture of not just hydrogen, it's mostly hydrogen, but also oxygen and sulfur in there, which can be colored in different ways to make it look amazing. Now, one of the structures, I'll zoom in here, one of the structures that is now starting to really appear is that area that you saw in the previous image taken by the space telescope. This area is where, as you can see, here's these structures, these gas structures that are coming out here. They're all pointing towards the center of where those stars are, because those stars are what's carving out these shapes out of the gas. They're really kind of blowing them away and molding them into these pillars and structures that appear. And inside of these structures, as we discussed, are where those stars are born. It's really an incredible, and you can see these structures are visible all around this nebula. Here are some structures here that I think in my previous presentation we may have talked about this, but some of these structures appear again from the same reason. They're all kind of pointing inward. I refer to this as the nebular zoo of the Rosette, because a lot of people see many different animals here. We've got a praying mantis. We've got, if this was more interactive, a kind of, it'd be a fun thing to see what people can see. But I see a panther here. I see a goat with its horns. I see a little dog with its tail over here. Here's the praying mantis, which would be hard to see. But anyway, so this is the type of nebula where stars are born. Okay, so I'm going to now leave this. I'm going to save this image first.
Ara,
yes,
a quick trivia comment.
Please.
The Rosette Nebula is the state of Oklahoma's official state astronomical object.
Oklahoma?
Yeah.
I didn't know that. Thanks, Russ.
Sure, just obscure facts here.
Wonderful. All right, let me quickly pause this. Stop. Go here. Sorry, I just want to save this so that I can send it to Andy afterwards, and anybody who wants this can actually request it. All right, good. So going back to the presentation. So now that we've talked about, what did I do this? Sorry about that. Now that we've talked about how stars are born, we obviously also talked about the different sizes of stars. So in our star is our beautiful sun that gives life and energy to our planet, is basically a perfect middle of the road, middle-aged star. It is fairly large, we know, compared to the pure number of stars out there. But as far as size is concerned, it's not the biggest star. Our sun, compared to one of the stars that we see in our night sky called Arcturus, it's a really bright one, this is sort of the rough relative size to Arcturus. And Arcturus, which is a very bright, big star, this is its relative size to the largest of stars out there, called the VY Canis Majoris. Now, there is some debate that this may or may not be the largest star, but it's the largest star that we know of. So our sun can fit into Arcturus 25 times, and our sun can fit into VY Canis Majoris roughly 2,100 times. So these stars can be massive. Now, why am I talking about different sizes of stars? And now we're going to have to endure this a little bit for just a tiny bit, and then you'll understand why. So all the elements that we know, yeah, I'm sure many of you know of hydrogen, helium, oxygen, carbon, nitrogen, all the things that we have on Earth. These are all elements that are born inside of stars. These are caused by fusion reactions inside of the heart of a star, and then expelled outward into the universe for other stars to be born out of. So what I'm showing you here is that the core of a star is where the heart and the fusion reaction happens. And initially, as I said, stars will start to fuse hydrogen to helium. And then if the star is slightly bigger in size, about say, a star about our sun's size will then also fuse some carbon and some oxygen as well. Stars that are about 4 times the size of our sun will then start to fuse oxygen. By fuse, I mean they're actually creating these elements, right? They're creating them from the lighter elements before that. So oxygen, neon, magnesium, sodium, those would be created by stars roughly about 4 times the mass of our sun. And then it just goes on from there, gets bigger. About 8 times the mass of our sun, we start to then create silicon and sulfur and neon and calcium and titanium and argon, all these other things. Now, the one really cool part of all this is that when you get to iron, it's not the end of our periodic table of elements, if you ever remember seeing it in class. When you get to iron, iron is the most stable element we have. The way, I won't go into detail, but the way iron, the little bits of iron, the little elements of iron, is the most stable element we have. So when a star has enough mass, and therefore the gravity is pushing it, crushing it down to actually fuse and make iron in its core, it actually needs to put in energy to make iron. With everything else before that, fusing oxygen, fusing hydrogen to helium, fusing carbon, it actually produces energy. That's what powers the sun. But now when you reach iron and you crush and you make iron, it actually doesn't produce energy. You've spent more energy doing it. And so the gravity is pushing down, and iron now is effectively the end of a star's life. Now, not all stars, as I said, will get to the point of creating iron. There's different types of endpoints. Russ, I know this is near and dear to your heart. Did you want to add anything here before I go to the next slide?
No, I think that's it. I think with stars like sun, the endpoint really is carbon. And, as I was showing here, an average mass star turns into a white dwarf. That white dwarf is, for something like the sun, is primarily carbon. And so you'll hear astronomers talking about diamonds in the sky that weigh millions of tons. That's really what they're talking about, is that it's the core of an average star after it's dead.
Yep. So an average star like ours, a beautiful sun, will ultimately, when it retires, I've been calling it dies, but it really isn't a death. It's just a transition to a different stage in its life. And so when it retires, it'll blow, it'll turn red, it'll expel its outer gases, and we'll see that in a moment. And it'll
No,
become,
no, it's pretty dead. It's not doing fusion anymore,
yeah,
Aaron.
okay. It just sounds so ominous when it's death. Well, okay, we'll call it death. It'll turn into what's called the white dwarf. So that core that remains behind once all the gases leave it, and we'll come back to a white dwarf. So I'm going to skip by this real quick because the next target we're going to look at is the gases that have left the white dwarf. A larger star will also bloat and become this bigger reddish star. And if it's massive enough, the core will turn into a neutron star, and we'll get to what that is. And then lastly, these very large stars that we mentioned, these huge blue stars that rock their way through their life and then die quickly, they will explode and turn into black holes, which I'm sure everyone wants to hear about. So the fate of a star depends on its mass. So how much gas and mass it has is how it drives how it's going to die / retire. So let's try to look at a nebula. Now I told Andy this is a bit of a oops. I told Andy that this is a first timer for this one. I have not imaged Medusa Nebula before, so it's going to be interesting to see if it works. So bear with me with a little caveat. We'll be seeing this target together for the first time. All right, so let me set that back in here. We're going to need first, this one's going to take a little bit longer to get going because first I'm going to need to, run this, which is going to move my telescope. I don't know if you can see here. I just like to show this to know that this is actually really happening. This is my telescope currently moving to the next target. It just finished moving. And now the computer's going to try to center it. So this is why I skipped the white dwarf portion, because I knew this was going to happen, the setup part. So when our sun, an average star, dies, it's not going to go out with a bang like we all hear about supernovae and all these great explosions that happen out in the universe. It's going to go out with a slow-ish death. Its outer, as the fusion engine stops creating as much energy as it is doing now, the outer layers will slowly start to expand and sort of drift away from that inner core. And as it does that, it will, the core will still be producing energy. So it's still exciting that gas as it leaves it, and it's not leaving slowly. It's going around 30 kilometers a second. So it's blowing out pretty quickly, but it'll blow out all the way past us, probably all the way to engulf the Earth at some point. And that gas will continue to expand at a pretty rapid rate until it gets so faint and dissipates out into the universe for it to join other gas clouds and new stars to be born out of that. So that will be the end of our sun. Now, those gas clouds that expand outward from these average sized stars, they are, oops, sorry, give me one sec. Forgive me. All right, let me now get this clear. Browse images, Medusa. All right, good. And we'll now proceed. Okay, sorry about that. So those gases expand, and they're still lit up by the energy of the star beneath it. So what we call those, and it's a total misnomer, we call those planetary nebulae. It is a nebula because it's still a gaseous form. They tend to be much smaller than the nebula we just looked at, but they're called planetary nebulae because when astronomers first saw these in their telescopes, this is a long time ago, they thought they were other planets. They thought these were just these really fainter or hard to see planets, and they often have these structures around them, which are lobes or they're circular in nature, and they thought they're just planets with rings and other things around them. So they called them planetary nebulae. They have nothing to do with planets, but they are nebulae that are effectively leaving the center, the core star in the center. So we have 8 images now. Again, these are 10-second images of this planetary nebula called the Medusa Nebula. And it's called the Medusa Nebula, and it's starting to come through here. Let me see if I can make the structure come out a little bit better. Again, this is being captured live with my telescope right now here from my front yard. All right, there we go. We're seeing some of the structure now. So it looks, it's a pretty small target for my telescope, but if you look at it, it looks like there's these filaments that look like snakes coming out of the central portion. That's why it's called the Medusa Nebula. Somebody named it, and it stuck. So yeah, this is a planetary nebula. Now, what I'm capturing here is the hydrogen gas. I'm using a special filter that really isolates the color of hydrogen gas as it's being lit up by its white dwarf in the center of it. There are other gases here that are also can be used to add color, but most of the imaging is done ultimately is done in black and white and then added together to form different color channels. But this is the hydrogen gas that we're seeing here, exactly as it appears in the night sky. Is there anything you wanted to add, Russ, to the dynamics or the elements of a planetary nebula that might be interesting?
It was William Herschel who first called them planetary nebulas. Herschel was observing in the 1700s with his sister Caroline, who is one of the best known women astronomers. And I would like to point out Caroline Herschel because it's International Women's Day. And Caroline actually did a lot of the calculations for William while he was observing. The first ones he saw were round, and he had observed Uranus and Neptune and knew they were round, and so that's why he called them, as Ara said earlier, that's why he called them planetaries. But we now know they have, as Ara pointed out, nothing whatsoever to do with planets. This one doesn't look particularly round because it's one of the older planetary nebulas that we know about. There are some other planetaries that look like perfect circles. There are ones that look like bubbles. There are people who, amateur astronomers, there are some amateurs who just spend all their time looking at these planetary nebulas.
I'm trying to see if I can isolate the signal a little bit more so people can see what it is. So this is a pretty small target, and that's what planetary nebulae tend to be. This is actually one of the larger ones that we have, because as Russ said, it's one of the older ones, and therefore it's blown outward much further. But a lot of planetary nebulae, and it was hard to find one for this particular presentation that's up at this time of night or at this time of the year. This is one of the larger ones, so it's nice to see. Okay, I guess I'll move on. And let me first save this image again so I don't forget. Stop. Save. Okay, great.
Ara?
Yes.
My name is Karen.
Hi, Karen.
Before we move on,
Mhm.
the name of that was, what was that?
Medusa Nebula.
Medusa Nebula. Okay, thank you.
You're welcome. Named after the Gorgon of mythology. All right. So now, that's right. I added this image because it was a last minute addition to image the Medusa Nebula. Here is a, I didn't give it credit down here, but this is an image taken by the European Space Observatory, Space Telescope, that of the Medusa Nebula. And of course, Space Telescope is pretty awesome. You can see all these filaments and all these structures here that made, whomever saw it first call it the Medusa Nebula. It really is quite an amazing structure. 1,500 light years away from Earth and spans about 4 light years. Remember, the other one, the first one we saw, the Rosette Nebula, was 130 light years in diameter. So, and that was 5,200 light years away. So quite a big difference. All right. So when an average star dies, its remnant, what it leaves behind is a white dwarf. Now, white dwarf, again, is what the end result of our sun is going to be the end result of our sun. A teaspoon of a white dwarf weighs about 5.5 tons. That's about the weight of an elephant here on Earth. Okay, so a teaspoon of a white dwarf star is about the weight of an elephant on Earth. And that's, a teaspoon of our sun doesn't weigh that much, but as you compress, as it gets older, the core compresses so much that there's so much mass to it that a single teaspoon is 5.5 tons. That is an incredible amount of mass crushed into a small space. They're very, very dense objects, and the white dwarf will roughly be about 100 times smaller than our sun is now. So it's still fairly large because our sun is very large, but it's going to be 100 times smaller and weigh as much, and a teaspoon would weigh as much as an elephant on Earth. Incredible. The most massive stars, so our sun will not go supernova, so there won't be this big bang one day. But our sun will, die, as we said, as a planetary nebula. But massive stars will go supernova, and anything from about 8 to, move this. Anything above about 10 solar masses, so 10 mass amount of our sun, anything above 10 times that will go supernova, will explode. So let's look at the next thing. So the middle one, remember, if in that diagram we showed you, those sort of large stars, but not the very large stars, those anything from about 10 times to 29 times the mass of our sun, those will go supernova, they'll explode. And so the way, even though our sun would die with the gas slowly sort of drifting away from it, supernova gases will come crushing down into the core, and then they'll effectively bounce off, and that's the explosion that we see in supernovae. So a neutron star, if the star is about 10 to 29 solar masses, that gas will come crushing down and it will bounce off it and it'll explode into a supernova. And what gets left behind is this thing called a neutron star. And it's a neutron star because all these elements that I mentioned to you, the hydrogen and the helium, all these various, carbon and oxygen, they're not really those elements anymore. Those elements have been crushed down themselves so much that they're not those elements anymore. They're even smaller particles crushed down into what is a neutral star. So, and a single teaspoon of a neutron star weighs 400 million tons. That's just a number that's completely incredible to even think about, right? 400 million tons. That's a lot of elephants. And remember, the white dwarf was about 100 times smaller than our sun. Well, a neutron star, which would have started off from a much more massive star, when it's crushed down, when the core is crushed down and the supernova happens, what gets left behind This neutron star is about 6 miles in diameter. That's about the size of a town. I don't know how, actually I should have checked to see what the rough size of Cape Elizabeth is, but it's not much bigger than Cape Elizabeth in diameter. Maybe from here to Portland. So that's what a neutron star would be. And the next target we're going to see is the remnant of a neutron star. The gases that blew away from a neutron star, and we'll actually see some of the remnant of that in the next target. Before I get to that though, because I always get this question when I do this presentation to all ages, is how does a black hole get created? And this is obviously an artist's interpretation of a black hole, as were the other ones, of course. But we finally just recently imaged a black hole, as you saw from the Horizon telescope event that happened a couple of years ago. But we won't necessarily talk about that. Now, a black hole is this mysterious object. We're still learning a lot from it, but it's basically even more of a crushing force than a neutron star, than the one before this. That whole teaspoon, 400 million tons thing, this is even more than that, right? So it had so much mass, and the gravity is crushing it so much that light coming out of it cannot escape. Light actually bends and gets trapped inside of this thing called an event horizon. So if you think about this edge as the event horizon, it's a black hole because light cannot leave it. Light just gets trapped inside of it. What we see here is called an accretion disk. So there's matter still falling into this black hole. It still gobbles up and shreds and tears apart stars that come near it. And it bends light from behind it, which is why you see this portion of the accretion disk. So the accretion disk is the matter that's sort of floating and roaming around it. And this is the backside of the black hole, with the light bent from it because of the black hole, and we're able to see that because of that bending of light. It's an incredible object. We are definitely certain they exist now, and we believe there's a supermassive black hole, million times the mass of our sun, in the center of our galaxy, and a lot of other galaxies as well. So that's how black holes get formed. Any questions, since it looks like people can unmute themselves, right? Andy, I wasn't sure if that was possible or not, but if there's any questions, please ask as we go along.
Yeah, people should be able to unmute themselves, and Russ has been handling a lot of the questions in the chat as well.
Oh, wonderful. I'm glad. Thank you. So now I'm going to switch and do our last target, which is called the Crab Nebula. This is M1 is its designation, Messier 1. So let me switch to that. And Russ, if you want to start giving some preamble around neutron star and the supernovae and whatever while I set this up, please be my guest.
Sure. So what Ara was saying earlier is that the magic word in astronomy is gravity. And so as stars die and they no longer have fusion, it really depends on how much gravity is there, which is dependent totally on the mass, like Ara said. So for stars like Sun, once they're done fusion, they cannot collapse atoms. And so a white dwarf is primarily carbon, like we talked about a little bit earlier. If there's more mass and there's enough gravity, atoms actually cannot exist. They actually get crunched together. And so all that stuff that you've learned in school about protons and neutrons and electrons, they all get crushed together, and the protons and electrons combine and form neutrons, and we only end up with neutrons. And so a neutron star is actually about the same density as the nucleus of a single atom, except it's 6 miles across. So if you can imagine the nucleus of an atom being 6 miles, 10 miles wide, that's what happens. With even more mass, like Ara said, it collapses. Even neutrons cannot withstand the force of gravity, and they collapse. There's some questions theoretically about whether we could have quark stars before we had black holes, because all of these atomic particles are formed out of quarks. And so it's highly controversial. I don't even know how we would observe a quark star. And interesting, if it's even more mass than that, the quarks can't hold themselves together, and that what forms black holes. So we really talk about two kinds of black holes, if you want to think about it. There are these ones that are left over from these supermassive stars that form black holes that might be the mass of 20 times the mass of sun. And then, as Ara pointed out, there are supermassive black holes that formed in the middle of galaxies. They probably form differently, but they can be many millions of times the mass of sun in the middle of a galaxy. And they form what are called active galactic nuclei that we can actually observe in various different kind of ways. So interestingly, we have actually observed stars orbiting around the center of our own galaxy, and they're moving so fast that the only way to explain it is they're orbiting around a black hole. So black holes are really interesting. And as Ara said, lots of people have lots of questions about them.
Okay, we're almost there, Russ, and then I'll start
Okay,
this.
I see it.
You see it. I just want to. It's almost done centering it. You'll see it now move from here to here. I should have probably stopped it before then, but oh well. It's called what the computer is doing right now is called plate solving, which is basically determining. It knows where this target is, and based on the stars around it, the computer nudges the telescope exactly to the point where this target will show up right in the center of my field of view, because that's where I wanted it to be.
Okay, while we're waiting for that, I'll tell you another kind of interesting little story. As Ara pointed out, this is called Messier object number 1. And Messier was observing in Paris in the late 1700s, and he was called the ferret of comets. And he was actually looking for Halley's Comet. They had predicted that Halley's Comet would return in the 1700s when this was first done. And they predicted that it would be in the constellation Taurus, the bull. And so Messier, who was the ferret of comets, was looking for Halley's Comet all through the constellation Taurus. And when he found the object that Ara's going to show us, he thought he had been the first person to recover the image of Halley's Comet coming back on its 76-year orbit. As it turned out, that was incorrect. It wasn't Halley's Comet. It was this other object that people could mistake for an object. And at that point in time, he decided that it would be a really good thing to catalog things in space that people might confuse with comets that really weren't comets. And how could he tell it wasn't a comet? It didn't move relative to the background stars. Comets move day by day compared to the background stars. So if you looked at it one day and then looked for it the next day, you would have seen that it would have moved. But objects like this one, the Crab Nebula, don't move. They're not in our solar system. They're way outside of our solar system. And so Messier started putting together a catalog of objects that were not comets. And they were the brightest fuzzy things in the sky. And to this day, amateur astronomers use Messier's catalog because they're very bright, because he was looking at these things with relatively small telescopes from the middle of Paris. And if you're an amateur astronomer and you want to go see what things you might be able to look at, the first thing people really jump on is the Messier catalog. And it was based on a mistaken identity of this particular object as Halley's Comet.
All right, Russ, we're stacking now. If you want to talk about the Crab Nebula.
So the Crab Nebula is actually a supernova remnant. And this is one of the more massive stars that, as we said, when it dies, first of all, it implodes, and then it blasts everything off out into space. and it will leave behind either a neutron star or a black hole. This one left behind a neutron star. And some neutron stars, because of what's called conservation of angular momentum, actually start spinning. And inside this nebula is a spinning neutron star. And so the outer portion that you're seeing right now are the gases that got blown off from the supernova explosion. And then maybe in just a little bit, we'll start showing you a couple of pictures of what you can see. How
Hey,
can
Russ,
you see a neutron star? Yeah.
sorry to interrupt. Of course it happens. The application I was using to live stack just crashed. So let me just get that up and running. I just want to make sure you understood why it disappeared on you.
Okay, well, let me, how about if I show the multispectral,
yeah, let's do that. Let's go to that. Since it's 7:20 and we want to still have some time for questions. So I'll switch back to that.
All right, so let me just take over screen sharing for a minute.
Oh, I was just going to bring it up for you. This?
Oh, okay. All right. That's great. So let's just talk about what we're seeing. Ara brought it up here. We're looking at images of this Crab Nebula with 5 different telescopes and 5 different wavelengths. So when you see this first red one, the red image is actually from radio telescopes. So we're looking at what this object looks like if we were just looking at radio waves. And then if you look at the yellow ones, the yellow image that's coming up here in a minute is actually the infrared image. So like Ara talked about earlier, that's longer wavelengths than infrared, longer wavelengths than visible. The green image actually is visible. And so you can see what it might look like in a regular telescope. That's what it would look like. The next one is ultraviolet. And that's this blue image coming up right now. And then the purple one is X-rays. So we've gone all the way from imaging this object with radio waves and colored it red, all the way up to these X-rays, which are colored purple. And then the computer stacks all 5 images on top of each other. That's what you see there. And so what you can see at the very end are this huge, massive amount of material that's been blasted out by this supernova explosion. And then finally, in the ultraviolet and X-ray images, you can see this, which is the pulsar. And you can see it spinning, leaving disks on the outside. This is really an amazing object. And it is still expanding. So from the first observations that really tried to look at this in detail in, say, the early 20th century, until now, the object has actually gotten significantly bigger, and we can measure how fast it's expanding. And it turns out it's expanding at about 0.5% of light speed, which is really pretty fast. So pretty amazing. So very interesting. So earlier people were asking about colored pictures. None of the telescopes take pictures in color. They take black and white images like the ones Ara was showing. And then we can assign colors to each one of these. So we assign red to radio, we assign purple to X-rays and everything in between as a color palette, so that when we look over it, when they're all stacked together, it's this absolutely spectacular picture of the Crab Nebula. I think one other thing that we haven't said yet tonight is it takes a supernova explosion to make elements heavier than iron. And so all the elements on Earth that are heavier than iron were formed in a supernova explosion. So does that mean that sun is not the original star? And the answer is yes. We think we are 3 to 5 generations of star birth later. And so our own solar system was formed out of material that had been in somewhere between 3 and 5 stars. And so all of the atoms in your body were made in stars 3 to 5 generations ago. And if you're as old as I am and you remember Joni Mitchell about we are all stardust, this is absolutely true.
And
okay, are you stacking now?
No, I stopped doing that because I think we're towards the end of the time anyway.
Okay.
So, and as Russ said, this little dot here in a couple of these that show up right right where my cursor is, that is the neutron star at the heart of this supernova remnant. So that's the star that exploded. That's the star that is causing this gas shell around it. That's the star that is has this little circular spinning nebula inside of it. Here you see in purple. That little nebula inside of it is the magnetic waves of this super dense neutron star spinning so fast. So that neutron star is spinning 30.2 times per second. So think about an object the size of a city, right? 6 miles in diameter. Thinking of a dense, super dense object, 6 miles in diameter, spinning so fast that it's spinning 30.2 times per second. And we can measure that. We can measure that because it puts out these huge magnetic waves that just excite all the things around it. And you can see the direction it's spinning here because you can see this donut-like shape around its center. Now this next bit, is a video that I'm hoping will play. Sorry. Okay, here we go. This next bit is a video that is taken over by a gentleman named Detlef Hartmann, taken over, I think, 10 or 12 years. Every year or every year or so, he imaged the Crab Nebula, and he stacked it together and aligned them perfectly so that he can have an animation out of them. Now, this animation is unique in 2 ways. Pay attention to the size of the shell of the gas. As Russell said, it's expanding at 0.5% the speed of light. And also pay attention to what you see in the middle. That donut that I mentioned, the magnetic waves of that neutron star spinning at 30.2 times per second, you can actually see what it's doing. And then it'll reset. It'll go 2 or 3 times. Let me move this so you can see the years. Sorry. I'm not sure why it comes out of it when I do it. Let me try that again. All right. Here we go. Replay. So 2011, 2012, 14, 15, 16. And you can see the center, that donut right in the middle there, swirling around. And the gas slowly expanding over those years. And then whoop, back down to 2010.
Do we know when it exploded?
Yes, it's believed to have exploded, and the Chinese were the ones who had, I think other cultures documented it as well, but the Chinese were the first to document it in, correct me if I'm wrong, Russell, in 1054 AD?
Yes, this is the famous supernova of 1054 AD. It was traced back to the Chinese. It turns out the Japanese may have recorded it a couple of weeks earlier. So this is one of the very few supernovas that we know exactly when it happened. There are some theories that even the Native Americans in the American Southwest did cliff paintings and things of this particular supernova. So this one's pretty well documented. In fact, after it was determined that this one was probably in the ancient Chinese writings, because the Chinese had 2 kind of astronomers, believe it or not. They had astronomers that observed things that didn't change in the sky, and then there was a whole different set of astronomers who only looked at things that changed in the sky, like the positions of the planets and supernovas and things like that. 7 additional supernovas were identified in the historical records, but nowhere near as accurately or as in many cultures as this one. This one was visible. It was such a bright supernova that it was visible unaided eye for at least 2 years, and was recorded in cultures throughout the world. So So we do know how old this one is.
Any other questions?
There are a few questions in here about gravity, and Russ, you started to answer that in the chat. I don't know if you wanted to talk more about that. Someone asked what causes the gravity that it all starts with. Where does that come from? And earlier someone had
Yeah,
asked.
so those are really interesting questions. It's like asking where the four fundamental forces of nature come from. And over the years, we've been able to develop theories that explain the three other fundamental forces of nature, not necessarily where they come from, but how they interact with each other. And then we have gravity. And so the other three, you'll hear people talking about quantum mechanics all the time. And the big thing right now is there is no good theory that can combine quantum mechanics with gravity. So it's going to take, in my opinion, somebody, some other genius on the level of Einstein or Newton to come along to be able to really come up with a reasonable explanation of how these other three fundamental forces of nature and quantum mechanics fit together with gravity. So it's a fundamental property. If we really got into particle physics, it has to do with particles being passed back and forth, and there are things called gravitons, and we haven't really even observed what we think gravitons would look like. So it's still pretty far out there. This is still an area of fundamental research in physics.
And are there
You want to
any
read the
other?
questions, Andy, if there are more?
I think Russ has knocked them all out of the park here. Unless people have some other questions, feel free. You can unmute yourselves or drop them right in the chat.
I was curious about your scope. What kind of scope do you have? How big is it?
It's a 5-inch refractor, 130 millimeter refractor, and yeah, it's an F. It's reduced to f4.3, I think. It's an Astrophysics Starfire GTX 130. Ask more questions. I don't know how much you know about telescopes or not, but that's the size of it. It's about this big in diameter.
Yeah, I'm more used to spotting scopes for birds.
Ah, it's a good size scope. I mean, I think refractors are sort of your general field. They give you the field of view that captures most of the objects out there. Some of these smaller things like planetary nebulae and Crab Nebula, as you can see, I'm zoomed in quite a bit to get it to show up well. If I were to do the full frame, you can see it's a pretty small portion of my frame here. So I would have used a different telescope to probably get all the details of this one in. But refractors are pretty good. Anybody else? I know you're dying to ask questions. This is your chance.
Well, if
All
nobody
right.
else does, so being very curious, I go outside with my binoculars or my spotting scope, and I look up and I see the Big Dipper, and then there's some stars near the Big Dipper or in the belt, in the Dagger, in Orion, and I can't find a place to go look and say, oh, what are these stars? Because they're either too complicated or not complicated enough. Is there a good place where I can go to try to find some of these stars to identify myself?
You mean by place, you mean some software or something that allows you to?
Software website.
Software website. Websites might be a little challenging. There are some free software that you can use out there for if you have a Windows computer. One of the free pieces of software that are really nice. They might be a little complicated looking at first, but you can get used to it pretty quickly. It's called Stellarium, Stellarium. It's free. It's got a really beautiful interface for navigating the night sky. And you can choose to include or exclude as much of the information that it can display to just the constellations. It has the folklore behind the various constellations and the arts and whatnot. So I'd recommend that for the computer. For the mobile phone, there's actually a bunch of different software. I use Sky Safari Pro, which it's allows you to, again, include or it's not going to show us blurred. Include or exclude as much of the items, and you can tap on the stars and it'll give you information about them. So Sky Safari Pro for mobile, and Stellarium for the PC.
Yeah, I have
and
Skyview, and it wasn't very good. I couldn't get the little stars.
Sky Safari is really good, and you don't have to buy the Pro version. There are, I think, 3 different levels of Sky Safari. So, you can, if you just want to go out and unaided eye do things, you don't need the real complicated Sky Safari Pro. That has all really dim galaxies and all kinds of other things in it. So, but Sky Safari Pro is probably, it's the one that I always tell my students about when I teach astronomy.
Thank you.
You're welcome. And you might need to download extra databases. I know in Sky Safari Pro, it didn't have the full, there's a lot of stars out there. So a lot of times they just have the stars in the default database. They'll have the stars up to a certain magnitude, and you'd have to download the other ones if you want the more and more faint stars. So just be aware of that.
And Karen,
Any other questions?
I saw that,
Sorry,
Karen, that you unmuted yourself. Did you have a question?
Well, yes. What I'm looking at is something that reminds me, what I'm looking at on my computer is something that reminds me of a CAT scan of a brain. Okay. So what I would like to know is, where did all those wonderful colors come from that you were showing us earlier?
Yeah. So think about it this way. If I'm right now taking this image using a very particular filter. So let's say if you had a regular camera and you took a picture of let's say you had a black and white camera and you took a picture outside with a red filter.
Yes.
And then you took the exact same, nothing changed, right? The leaves aren't moving, nobody's walking by. Exact same thing with a blue filter, and the exact same image with a green filter. So those three, now you have 3 images that are filtered based on those light, those filters that allow that particular light to come through. Now, if you take those red image, blue image, and green image, they would all look black and white to you, right? Because they're just one color, they're monochrome. Now, if you take all of them and put them together into what's called a color image, an RGB, red, green, and blue, then you have color. That's how you get a color picture. You take 3 different monochrome images using different filters, you add them together to produce a color picture.
So it's the camera. So it's the camera. It's not.
It's the camera and the filters you use to isolate a particular signal versus another.
If I could jump in here a minute. We normally use a filter for astronomical imaging because of the resolution. And so the performance of an actual color camera, like you might just take one, there are things called one-shot color cameras, but the resolution and the color imaging and your ability to manipulate those images is not anywhere near as good as you can do by taking the images like Ara just said. So because there are a lot of corrections that need to be done, and then all these spectacular Hubble images have been done by assigning very specific color palettes to the wavelengths that the cameras in the Hubble use. So the Hubble might be using 7 or 8 different black and white images that have been colorized to form one color image. at the end.
Okay.
And it also allows us to assign colors to those different wavelengths. So for the image that we showed with the 5 that were being stacked, you could only see one of those with the unaided eye. The other 4 aren't visible to human eyes. Human eyes are only respond to a very, very narrow part of the spectrum. So by being able to use other kinds of instrumentation and then coloring them, it's called false color imaging, we can see how all of those things play out together in ways that we wouldn't be able to see with our unaided eye.
Well, Ara and Russ, I want to thank you guys again so much for being here and doing this. This is always mind-blowingly just fantastic.
I agree.
You're welcome.
Yeah.
Yeah, absolutely.
Thank you.
And if any other questions come up, you can go to the Southern Maine Astronomers website, and there's a contact us form at the bottom. Just search for Southern Maine Astronomers. We have a website, and at the bottom there's a contact us form. If you have any questions, if you have any thoughts or anything you want to learn more, please don't hesitate to contact us. Several of us get those messages, and we're always eager to respond. Thank
Great.
you all.
Thank you so much, Ara. Thank you, Russ. And we'll see you in 3 months.
Okay.
Thank you.
Sounds great.
Thank
Thanks,
you.
Thank you
everybody.
all.
Thank
Bye,
you.
everyone.
Have a great night, everyone.
Bye-bye.
Thank you.
Bye. Thank you so
Thank
much.
you.
Thank you.